Okay, so in this last lecture, I would like to talk about the process of developing software. So we talked a lot about software, about individual algorithms, about parallelization. I talked to you about a few things, how to debug programs, for example, how to document them, and so on and so forth. But I would like to put this into a bigger picture. So in this 43rd and probably last lecture, I would like to talk about the issues that you've encountered when you develop large-scale software. So you remember when I talked about this in the last lecture, HPC, high-performance computing, is not just algorithms and their analysis, but it is really about applications. So when we talk about software for applications, that, let's say, that implement the methods to solve particular applications, we need to ask a whole sort of list of questions. For example, how complex is the software? How do we write software? Are there tools that help us with this? How do we verify that the software is correct? How do we validate that the model that we're solving is correct? And then how do we test software? How do we document it? And there's an issue that I would like to talk about at the very end, about social issues in dealing with software. So let me go through some of these points in the next few slides. So most of you are probably going to be students or postdocs. The software that almost all of you will have seen so far is software that you have written or that maybe some of your colleagues have written. And it is typically, let's say, a few hundred, maybe a few thousand lines if you're productive and you like software, then maybe a few tens of thousands of lines. In real applications, software is orders of magnitude larger. And just to give you an example, or three examples here, as of 2011, deal.II had 550,000 lines of code. Today it has approximately 600,000. One of the libraries that we built on for parallelism is called PETSI, and it has 500,000 lines of code. Trilinos has more than 3 million lines of code. And if you think about software development at this sort of scale, you realize that that doesn't work the same way as it does when you write your own programs. Namely, not a single person can have a global overview of this much code. I mean, I wrote a fair share of deal.II. Many others have contributed to this, but there are certainly areas where I have no idea. Every time I find myself struggling with the interface between the finite elements and FA values, for example. I didn't write this part. It's not poorly designed. I just don't know it. I have never had the time to look into it. There are other parts of the library that I'm much more proficient in. Similarly, if you think about the time it costs to develop this much software, this is many years. A good programmer can produce, let's say, maybe 100 or 200 lines of code per day with documentation. So deal.II would be approximately 5,000 days of coding, maybe 6,000 today. 6,000 days at 200 days per year would mean 30 years of work, 30 years of effort. Even if you, as a single person, would have done it, you would not remember what you did 30 years ago. I mean, deal.II isn't as old. deal.II started 15 years ago. It's not that a single person could have possibly written it, but the point I want to make is that it is impossible for a single person to know it all. And of course, even you yourself will typically not remember what you did, why you designed the algorithm like this, maybe just a half a year ago. So that gives constraints on, let's say, how much you can remember, how much knowledge there is in a project by the participants of this. It shows, for example, that you do need to document. There is no other way than documenting, because otherwise that knowledge will be lost. And you may remember, if you look at one of your own codes, just a few months later, if you didn't document it, sometimes you just scratch your head and you think, well, what's this doing? It's not even that it looks wrong. I just have no clue what it does. And so these are issues that you face on an enormously larger scale when you write, let's say, software for real applications, just because it's so much bigger. So it's not just about documenting it, it is just the complexity of it. If you were to try to understand a piece of code because you need to extend it, for example, and it calls into all sorts of other parts of the software, then that's just a lot of software that you have to understand. And the strategy that we use in almost all big projects today is that you have to what we call modularize. So different people work on different parts of the project, and they interact through very well-defined interfaces. So for example, you do not need to understand how a linear solver works when you write the triangulation class. And the other way around. That means that I can write the triangulation class, for example. Somebody else can write the linear solvers, and all we agree upon is that the triangulation class is going to offer this set of 5 or 10 functions, for example, that you can call. And the solver person agrees that there is this set of 5 or 10 functions that you can call from a solver. Of course, the triangulation internally has a much larger set of functions. There are hundreds of functions that are involved in this. But you define as small as possible set of interfaces that makes it easy to interface with a particular module, and then all you really need to know is the interface of a module, and then there's going to be a person who knows the internals of this module. But you don't need to know the entire set of all functions in a project in order to work with it if you're good at modularizing. Like I said, you need to document. If you don't document, there is no way you can understand a program. I recorded a whole lecture on documenting. And then what it turns out is you need to test as much as you can. If you don't test, software will not be correct. When we write software, there is essentially a single prime directive that is second to no other idea in software development, namely that developer time is the single most scarce resource. That is an absolute truth. There is nothing that is more valuable than the time of a software developer. So if you think, for example, today, even as a graduate student, you could probably buy on the order of 3 very large compute servers for what we just pay in salary for a single graduate student. CPU time, in other words, does not cost anything. If I can buy you a computer that saves you 3 months of time because it allows you to run a tool, then I'm going to do this. It's more important that you get your work done than that your program runs particularly fast or something. So make that the prime directive of your own work, namely that your own time is the most scarce resource. And there's a number of consequences that come from this, namely you should not reinvent the wheel. If somebody else has already implemented something, use it. I mean, it might very well be true that, let's say, I think that I can make our own linear algebra, let's say, on a single processor, run faster than, for example, the PETSI people can do it. But it doesn't matter, right? Because in order to make it run faster, I would have to spend time, I would have to implement, I would have to test, I would have to benchmark, and so on and so forth. It's going to cost me months to make this work, right? Are these months well spent? Well, maybe if I were to run problems that were going to use thousands of cores 24/7, then maybe it is worth to optimize my program. Short of this, I should just use what somebody else has done, right? Because it's the best use of my time to just read the documentation of PETSI and use it for my own project. That's a much better use of time than to try to implement it myself. You will find that it costs almost always much, much more time to implement something yourself than use what somebody else has used. Secondly, use the best tools. I've given many lectures in this series about, for example, Eclipse and Visit and Peer Review. Don't get stuck on something that is not the best tool for the purpose. If you're still programming in VI, well, God bless you, but that's really not a good use of your time. Use a much better tool for this because it will save you time, right? Even if it saves you only 5 minutes out of an hour, it's worth it. because your time is the most important part of the project. Then don't become the bottleneck. So what we often see in projects that are not good at documenting is that, let's say you wrote this initially for yourself, but suddenly there's 10 people who are using it, or in the case of deal.II, a few hundred who are using it. If every one of these few hundred people sends an email once a month to the mailing list because they can't figure out how this or that works, and I think one a month is not actually a very large number. If that were the case, we would do nothing but answer emails. Because in that case, we have gotten the bottleneck. The people who did not document their code have become the bottleneck for the entire project. You will get to do nothing else but answer emails. So don't make yourself the bottleneck. You have to delegate this somehow. One way to do this is to document it properly, because then people can read up on by themselves. Train other people in it, train them to answer emails on the mailing list. If there are questions, maybe you should spend the time in explaining it to a few so that next time they can explain it to somebody else. Okay, second set of consequences. Reuse code. If you've written, if somebody else has written code, or if you have written code, use it, don't duplicate it. Use strategies to avoid introducing bugs. I told you in one of the lectures that we use a strategy called defensive programming because we do realize that we create bugs, that we introduce bugs. And so listen to yourself, try to figure out what it is that you do wrong, and try to use that as a learning tool to figure out how to do better next time, right? We make the same bugs over and over again, and it's worthwhile figuring out what the kind of bugs are that we make and how we can avoid that the next time. So defensive programming is essentially a strategy how you figure out what you do wrong all the time and how to avoid that in the future. Then in several of the other lectures I talked about debugging, and that even good programmers make bugs and spend far more time debugging code than writing it. It turns out that it takes far more time to find a bug if you wait for finding it. The easiest way to find a bug, the most efficient way to find a bug, is you write your code, you write a test, you verify that the test works. In practice, it will never work, but then you go write about fixing the bug, and then when you know that the bug is fixed and the test works, then you check it into the repository, for example. If you write your code, and then you write some other code, and you write some other code, and then you write your application, and the application doesn't work, you don't know where the bug is. It might have been in any of the pieces of code that you've written in the middle, right? So it turns out that it is much more efficient if you test your program, or if you test your code right away. That's what you need to do, because it's the only way to be efficient about debugging. So once you have a code that solves something, there are two approaches that you need to do to verify that what you do is solving the right application. I mean, we're not talking about, let's say, solving the Laplace equation, but let's say Patrick's drill. These two pieces are typically related or called as verification and validation, or V and V for short. So verification refers to the process of making sure that the program solves the problem correctly. So what that means is that, let's say we have identified that the smallest displacement elasticity equation is the equation we want to solve. So what we need to do is we need to implement a linear elasticity solver. And we would need to verify that, yes, it's called, yes, it is. I keep confusing verification and validation like everybody else. We all get confused. So the process that we need to do is called verification. So we need to verify that our program really does solve the elasticity equation. So a typical way would be you solve a problem on, let's say, the unit square, where you know the exact solution. You run your program, you make sure that the solution that you get is correct, that it converges to the exact solution. That's the process of verification. And a common strategy to achieve this, of course, is to test, right? That we write unit tests that verify that every single function is correct, for example. That we write integration tests that the whole algorithm works as expected. For example, we compare with a known solution through a technique that is often called the method of manufactured solutions. If you want to look up what this means and how it works, go to the frequently asked questions. Then we would write regression tests that verify that the output that we get today is the same as the output that we get tomorrow. And I want to sum these 3 points up essentially in the following statement, namely that software that is not tested does not produce the correct results. And you will notice that I don't say that software that is not tested may not produce the correct results. I say that it does not produce the correct results. I think everybody who has done large-scale software will tell you that if you don't test, the answer will not be correct. No way. Answer will not be correct. You need to test. Okay, so the second step of this V&V process is called validation. Validation refers to the process of making sure that the program solves the correct problem. So the first step was the programs. Let me show you the 2 statements. The first part, verification, is that the program solves the problem correctly. And the second part, the validation, would be the program solves the correct problem. So the first one would be to verify that we have correctly solved the elasticity equation. The second part would be to validate that the elasticity equation is indeed the correct equation for the model, or let's say the correct model for this particular problem, that a drill in this regime that we're looking at does behave elastically, does not show plastic behavior, for example, does not show hyperelastic behavior, and so on and so forth. So I'm not going to talk very much about validation because this is a process that goes far beyond what we want to talk about in this class. Essentially what it means is you have to solve the equations that you have verified are correct, let's say the elastic model, and you need to compare it with actual experimental data and verify that your model that your solution comes close to the actual experimental data that you have. Right, so that requires going out of the computational realm and comparing with other things, with other data that you have. That's what validation is. Okay, let me talk briefly about testing. So I would like to repeat the fundamental truth about software, namely that software that is not tested does not produce the correct results. It does not produce the correct results. Not may not produce, it does not produce the correct result. And I think all of the big projects that do software have realized that and do test a lot. The only way you can achieve correctness is if you test. So in the case of deal.II, for example, back in 2011, we had approximately 2,300 tests. Today, it's, I think, 2,800 or so. We have a repository. We talked about Subversion and Git. We have an SVN repository that tracks all of the changes that we make. Every time somebody makes a change, whether it is a big new algorithm or just a typo fix in the documentation, every time a change happens, we run the entire test suite of all 2,800 tests. Back in 2011, this took approximately 10 CPU hours. I think today it's probably closer to 12 or 13. So there's a machine that has 8 processors that does nothing but just run the test suite every time we make a change. And then it sends its results to a website where we can see of all of these 2,800 tests, do all of them produce exactly the same output as they did when the test was written? And if they don't, then we know there is a problem. Then that means that a particular change that somebody had checked into the repository produced or made computations differ. And then you have to investigate. Are these differences just, let's say, in the 16th digit due to floating point roundoff, or are they substantial? In any case, you have to investigate this. If you don't do these sort of things, you will eventually change functions that used to work and break them. They will work maybe for the case that you have in mind when you changed it, but they might not work for the original case anymore. And somebody's program will rely on this and will not work anymore. That might be very hard to find out what the problem is, because let's say people build applications on top of deal.II. If deal.II changes its behavior, the application might not work anymore, or might just produce different results that are possibly not correct anymore. So you have to do these sort of tests. Like I said, 2,800 tests right now. At the time the test suite had on the order of 250,000 lines of code on top of the 550,000 lines of code that deal.II had itself. So the test suite is a very substantial fraction of the code that we actually write. Documentation. I talked about this in more detail on another occasion, that you have to write documentation at multiple different levels, functions, classes, modules, tutorials, that they spell out what the implementation does, not how it does it, and so on and so forth. So I'm not going to go into this much anymore in more detail. The last thing that I would like to talk about is social issues. So deal.II is a project where we have well, maybe half a dozen people who regularly commit stuff into the repository. And then there's maybe 2 or 3 dozen people who occasionally do so. So this is a community of people, and we have to get along. I mean, we're not machines. We have feelings. We talk to each other. We get along, or maybe we don't get along. All big software that you will work with in real life, let's say in industry or in the national labs, is written by multiple people. And it turns out that some of the most difficult to manage problems in software development are not technical. They're not of the kind, well, gee, how do I make this algorithm work not just on 100 but on 500 processors? Or can I reduce the number of Newton iterations from 15 to 10 by using a better line search, for example? So these sort of things, these are technical issues. This is something that we're good at. I mean, we know how to deal with this. We know possibly who has the right knowledge. We identify the person. We talk to them about the details. We figure it out. We implement it. It works. Okay. What we often have much more problems with as humans, maybe more as computer programmers than some other people, but certainly any kind of person finds that this is difficult, is the social issues. And I've listed a few of these things here on this slide. So, for example, let's say one of my colleagues has written a piece of code. Can I just modify this? Can I change his code to use a different algorithm, or to use a different indentation style, or maybe can I change these variables? Because people have pride and ownership in the code that they write. I certainly am proud of the code I write. How do I feel about it if somebody else just comes along and changes my code? So we need to consider these sort of feelings that people have for the code. There's a statement that was made in the 70s, I think, that it turns out that people who have pride in the code but don't feel territorial about it are much better, or let's say teams where there's not territorialism, where people allow others to change code, are vastly more productive. Because I mean, I think I feel this way about deal.II as well, that yes, I think by and large I write good code, but if somebody else comes along and improves the code, well, that's great, right? That's great for me too. I like this, but I do struggle with the fact that they may have different conventions, that maybe they use only one-letter variables, which I personally don't like. So there are personal attachments to code that we have to take into account, and I can't just barge in onto somebody else's code and change it radically. They might have, let's say, ownership feelings for this, and that leads to social problems, right? More examples. So let's say my colleague X just modified this piece of code, but he didn't update the documentation and didn't write a test. Okay, very common case. It's very difficult to tell people that it's just as important to write the documentation and to write tests than it is to write the code in the first place. How do you deal with this as a project? Similarly, let's say a colleague Y1 has, or let's say student Y1 has written a great piece of code, but it doesn't conform to the coding style that we use, and he's unwilling to adjust it. He says, well, I wrote a great piece of code. You know, you can have it, but it's your choice what you want to do with it. How do you deal with this? I mean, I think experienced programmers realize that you have to use the coding style of a project. You can't just impose your own coding style, because if you do, the code is going to look like a mess, right? I mean, some pieces of code are going to be indented by 2 characters, others by 8. Well, you can do this, but it doesn't make the code easier to read. So if a student is a good programmer but doesn't understand these dynamics of large-scale software, how do you deal with this? This is a human problem. We've had these sort of problems where we say, can I ask you to please change the code in this particular way? And they said, well, go away. I gave you the code. Don't bother me. That's a social problem. Right? Similarly, let's say I have a student Y2 who seems clever, but who may still have a little bit to learn. So the code is not quite up to task. Maybe it doesn't cover corner cases. If I tell the student, you know, we can't take this code until you fix all of these corner cases, chances are, certainly in a volunteer project, that they're going to go away. They say, well, you know, I did what I could. If you bother me, I'm just not going to send you any code anymore. How do you deal with this? So my approach to this is oftentimes I take the code, I fix it up myself, I send it back to the student and say, okay, so I made these changes here, for example, that are necessary for these and these reasons. Can I still check this in under your name? Okay, so this way the student gets credit, but I had to do the work. The hope, of course, is that by showing the student what I did and why, that the next time they submit code, they think of these sort of issues right away, right? And it turns out that a lot of the contributors of deal.II came to deal.II this way, that they sent code that somebody had to fix up a little bit and mentor them a little bit. This, again, is not a technical problem, it's a social problem. How do you encourage people to keep coming back to a project? Or in the case of, let's say, if you're in a company, how do you keep them motivated to keep working on it without telling them, you must do it this way? Okay. Second to last problem. Let's say colleague Z has written a great piece of code, but it does have a bug. Happens to everybody. And he agreed to fix this bug because I need it in my project, but 3 weeks have passed, nothing has happened. If this colleague Z is somebody I pay, I have a handle on it. But if it's a colleague who is paid by a different project, for example, or who works for a different university, I have no handle on this. How do I deal with this? How do I talk to people in such a way that they're willing to work with me on this? And then a not uncommon problem is that somebody has written some code, you send emails, and they just refuse to answer. That too is a social problem. So you see that when multiple people work together in a project on large-scale projects, that social problems are actually the much more difficult problems that you have to deal with. Technical problems, we know how to do this. You have to debug it, you have to test it, and so on and so forth. Social problems are often very difficult to solve. Maybe there is no solution. Maybe you just have to do the work yourself. Or in rare cases, you have to tell somebody else to go away. We don't want you in this project anymore. So these are just things that are really awkward, and I hope what this slide gives you a little bit of an idea with is that if you work with others, that you have to somehow figure out how to do this. My colleague Timo Heister and I wrote a paper on what makes open source projects successful that deal with some of these sort of questions. How do you engineer a community? How do you make a project welcoming to newcomers, and so on and so forth. So with these social issues, I will leave you. I've recorded 43 lectures. If you've made it so far, you probably know every single one of my polo shirts, for example. And I hope you have learned something. Feel free to join our project, deal.II. Feel free to send me personally comments about this lecture if you have any. And otherwise, I hope that you learned something.